Hi! If you have clicked on this video, chances are you are familiar with the Factorio solar panel mechanics. If your current save file is into megabase territory, you might have even developed some trauma from your UPS crashing after suddenly pasting down blueprints with tens of thousands of these things. I'm sure you've heard before about the so-called perfect ratio of accumulators to solar panels, and how the Space Age update turned it from a manageable 21/25 or 0.84 to a hellish 2646 over 3125 or 0.84672. People really like to discuss over how close their setups get to this number, but in fact that's only one part of the story, and focusing your design too much on just nailing the ratio tends to result in usable floor space being wasted. Then there are players who prefer symmetry or simply prioritize how things look from the map, and some focus on making a tileable blueprint while others just place the panels wherever they fit. Is there an optimal design then? Well, for that question to have any significance at all, we first need to define what best actually means. In this video, I'm going to use these three conditions. First, a fixed tileable footprint, like a 50 by 50 square. Second, logistic network integration, so we can blueprint and scale easily our design. And third, a quantitative metric, some figure we can compute and rank designs with. It then follows naturally that this metric should be the continuous power that the solar array can produce, i.e. how big of a continuously running base we could support with our fixed footprint design. Is there an optimal array under these conditions? Well, the answer is yes, and in fact, I found it. Here it is. Although, in all honesty, it wasn't me who found it, but rather a mixed integer linear programming solver. But let's not get ahead of ourselves, we need to cover a lot of math before we get to that. I included chapters on this video, so I won't judge you if you jump ahead, or if you just want the blueprint, which you can find in the description. But I encourage you to keep watching, there might even be a few things you didn't know about Factorio. Let's start with the very basics. We can represent the world of Factorio as an infinite arrangement of 2D tiles, where buildings can be placed to occupy that floor space. A solar panel is a building with a 3x3 footprint which generates some power over time depending on the light level. Power is constant and maximum during the day, zero during the night, and increases or decreases linearly during dawn or dusk. Peak power depends on the planet the array is installed at and the quality grade of the solar panel building itself, which can further scale up the production up to 2.5 times. On now BIS and working with base qualities, a solar panel produces a peak power of 60 kilowatts and an average power of 42 kilowatts. Most of the analysis in this video will be limited to no BIS and will be working with base qualities. However, I'm giving you the tools to work out the ratios and setups in every other case. Now, supposing our factory operates continuously at constant power, we cannot expect to draw more than the average power from a solar array. Otherwise, throughout a day, our energy consumption would be more than the energy that solar panels can generate. So there is this rule that maximum continuous power can never surpass panel average power. However, that's not the only limiting factor, as we need to store the extra energy generated during the day to keep the lights running during the night. To do so, we need accumulators, 2x2 footprint buildings capable of storing up to 5 megajoules each. Similarly to solar panels, this value is dependent on the quality grade of the building, which can provide up to a massive 6-fold increase in capacity. As mentioned, most of this video will be limited to base quality, but in the interest of generality, we will keep this in mind. Just to verify, let's run a quick test with a single solar panel, an accumulator, and a 42 kilowatt constant load. And yes, I did mod the radar to consume exactly 42 kilowatts. As you can see, things cancel out perfectly, and after a complete day-night cycle, the accumulator dips and then slowly charges back up to full. Crucially, however, the accumulator is not fully discharged at any point during the cycle. Even at the lowest point, there are around 0.8 megajoules left. The extra charge is, in a way, being wasted. We could get away with having less maximum capacity and still maintain peak power. When we divide the capacity that we are really using by the total charge an accumulator provides, we get the perfect ratio. That's where it comes from. For each solar panel, we don't need an entire accumulator to maintain constant power. We just showed empirically that 84.672% of an accumulator is just enough. Now, that's all well and good, but I promised a formula that works for all planets and quality grades, and you are definitely getting one. To do that, we need to find an expression for the maximum continuous power we get from our setup. As we discussed before, we already have one upper limit on that, as we can never draw more power than our solar panels produce on average. But then there's another limit on top of that, because during the night we cannot consume more energy than what has been collected in the accumulators. The total charge they can store is just the number of accumulators times the capacity, and we know power is energy over time, so the maximum power they could be drained at is the total energy over the amount of time the accumulators are running, which we can represent as a fraction of the total day length. However, it is here that we encounter a small hurdle, because in Factorio the switch between day and night is gradual and the accumulator provided power is not constant. So for our formula to make sense, we need to find some way to define the duration of the night. And for that we need to figure out some equivalent system where the total energy provided by the accumulators is the same, but they always work at full power. Visually, it's relatively easy to see that we could reach that equivalent system if we take this triangular section right here and place it over here. Then the duration of the night is just the width of the rectangle, which comes out at exactly 0.24. And just so nobody can complain in case there's some deranged modder out there who decided to change the solar power curve, here's an actual generic formula to back up our geometrical reasoning. As you can see, it involves an integral over the duration of the day, where eta is the delay-dependent solar efficiency we saw before. In fact, to be even more accurate, we would need to consider that Factorio is a finite step-size simulation where within each tick, values stay constant. So we would need to replace the integral with a sum over all ticks within a day, but really do not worry too much about that. The really important thing is that this 0.24 value is a non-dimensional quantity, which means it can only depend on the shape of the solar power curve itself. So, in fact, this is a kind of universal Factorio constant. It's the same for all planets, and even across all versions, since the dawn and dusk fractions have always remained the same. With this in mind, we can now complete the formula for the accumulator limit, and we can safely say that the maximum continuous power a solar array can provide is the lower of these two quantities. If A is greater than B, then there is solar panel production capacity that is being wasted, and on the contrary, when B is greater than A, we are running a solar panel limited array, and some accumulator storage capacity is going unutilized. So it follows naturally that both quantities need to be equal for peak efficiency, and if we try to isolate the ratio of accumulators to solar panels, we finally get the formula we wanted. Now we can quickly check with our novice values to make sure. And yeah, as expected. So you can go ahead now and plug whatever quality or planet dependent values you want here. For example, we can go to Gliba, which has a peak power of 30 kilowatts and a day duration of 10 minutes or 600 seconds, with legendary solar panels and rare accumulators. If we plug the appropriate values in, we get a ratio of 0.504. Or if just for giggles we want the smallest value possible, we can go to Aquilo with a day duration of 1200 seconds, a measly 0.6 kilowatts of peak power, and choose legendary accumulators over common solar panels to get a ratio of 4.032 times 10 to the minus 3, which means a single accumulator can support around 250 panels. Anyway, even if the formula for the ratio is useful, what we truly care about is the maximum continuous power. That's what we are going to use to compare our full array solutions. Yeah, remember what this video is about? Unfortunately, before we get to that, there are still some sources of complexity we need to cover, namely the electric network and the logistics. Let's start with the latter of these two. For expandability reasons, it is extremely convenient to include roboports in our solar array, and this is the requirement that defines the tileability of the design, as at least we need one roboport in there. So it's very common to see designs that roughly fall within two main sizes, 50 by 50 unit cell and 100 by 100 unit cell. In this video we will stay mostly at the slightly less efficient 50 by 50 cell level, and we'll leave the 100 by 100 cell for another time. In any case, the roboports don't really produce power, so once the array building stage is complete, they are no longer useful, and so for the sake of efficiency, the best we can do is replace them by 4 accumulators. So the best strategy is to design slightly accumulator poor, so that optimal power conditions are reached when the roboport is replaced by 4 accumulators. Electrics, on the other hand, are the silent killer of efficiency in solar power array design. Every substation we place is setting us back 4 valuable tiles, which could be used instead to place a power generating or storage component. Most designs out there tend to disregard electrics, because they don't really hurt the ratio, but remember, we should not optimize for the perfect ratio. What we need to optimize is maximum continuous power, and the more area we lose on electrics, the less usable space we get for solar panels and accumulators. Compared to the logistics, electrics are much harder to design optimally, and there's a whole bunch of conditions and restrictions that need to be met for an electric network to be valid. We are going to tackle it slowly, but for starters, there are 3 fundamental rules our electrics need to comply with. First, coverage. Every solar panel, accumulator and roboport needs to be covered by the electric network. Second, connectivity. All elements of the electric network need to be part of a single connected graph. Connectivity islands are not valid. We need the whole array to be covered by just a single network. And third, tileability. The electric network, as the full array itself, needs to be tileable. If we place another blueprint to the side of our original array, their respective electrical grids need to connect. On top of all of that, as we mentioned, the network needs to be minimal. The fewer components, the better. In Factorio, there are 4 different buildings that can form part of an electrical network. These are, in order of unlocking, the small, medium and big poles, and then the substation. As you can see from their stats, small poles are inferior to medium poles in basically every regard, so we can forget about them. Same goes for big poles. Their range is massive, but we don't really need it, and the coverage is terrible. And now, here comes the tragic thing. I wish I could say that the medium poles were useless too. It would make optimization so much easier, and we could get rid of so many edge cases, but no, they need to stay. You see, even if medium poles are worse than substations in terms of coverage per footprint tile, they do have significant geometric advantages because they are 1x1 tile buildings. We cannot simply discard them. In fact, my optimal design, and I promise we'll get there eventually, sit tight, contains medium poles as a fundamental and irreplaceable part of the network. So they basically get to stay. We are ready now to start solving the problem, but before we jump in with the numerical tools, bear with me just a little longer because we can simplify things analytically. Any simple factor property we can demonstrate beforehand will simplify things down the line a lot, trust me. On that line, let me introduce to you what I'm calling solar array design charts. We can construct them from the knowledge that in our 50x50 we have a total of 2500 tiles available. Then, if we select the number of panels and the number of substations, we can use our formulas to compute the optimal number of accumulators for each case and the available spare tiles, if any, which could be potentially used to place medium poles to help substations or just left as empty space. So, for example, if we were trying to make an array with 198 panels and reserved space for 8 substations, the optimal number of accumulators would be 168, and that would leave 14 tiles remaining. And by the way, we are making up for the Roboport with 4 of those accumulators. Just to add a little bit more data to this chart, each block is colored according to its maximum continuous power, so this chart is giving us an idea of the meaningfully different solutions that could exist. Now, if we go back to our example, we could potentially use those 14 remaining tiles to place one more solar panel. That would bump us one more column to the right. And then a solar panel costs 9 tiles, so we would have 5 tiles to spare. We could use those 5 to try and fit one more substation to go from 8 to 9, which bump us up one row, or we could try to place another accumulator, which results in a bit more power. Either case, we use 4 tiles, so we would have 1 remaining. Can you see how the diagram works? The chart, however, does not tell us whether or not the configuration is actually feasible, it just shows the power in the best case scenario. So consider the block we just mentioned. Yeah, the total number of tiles adds up to 2500 alright, but the pieces might not be compatible enough to fit together in the 50x50 square. The blocks at the top right corner are very heavily accumulator limited, so in general there tends to be very few spare tiles, and some configurations might just not be feasible. Something that has 10 or more free spaces is basically guaranteed to be doable in some way or another, but when we get below 5, some configurations displayed here might be just red herrings, which cannot exist in practice. In a kind of plot twist, I did find a mathematical way to demonstrate that some of these configurations are actually 100% impossible, and the proof is kinda cool, so we're going to cover it quickly. For the sake of my animations, I'm going to show this with a smaller 10x10 grid, but this applies to any even-sized grid. Anyway, the total number of tiles is 100. Imagine now that we wanted to color the grid using a 4-color pattern. Then I guess we can all agree that there are 25 tiles of each color. Now let's place down an accumulator. As you can see, it sets us back 4 tiles, and importantly, independently of where we placed it, it always takes 1 tile of each color. We can say that the accumulator is 4-way parity neutral, because placing it down does not impact some colors more than others. Because they also have a 2x2 footprint, the same goes for substations, and as I'm sure you can guess, the same is true for roboports. They just cost 4 of each tile instead of just 1. Now look at what happens with the solar panel. If we place one down in the bottom left corner, you can see that it sets us back 4 reds, 2 blues, 2 greens, and only 1 yellow. If we move it around, you can see that the color counts also shift. That means that the solar panels are disruptive to the 4-way parity. And actually, there are 4 types of solar panels according to their color counts. Similarly, the medium poles or empty tiles also upset the 4-way color balance, and just as solar panels, there are 4 types of 1x1 buildings, depending on whether they sit on a red, blue, green or yellow tile. So, given that solar panels and 1x1 tiles upset the balance, but everything else does not, we cannot place panels wherever we please. We need to place them in a way that their effects on the 4-way parity cancel out. For example, if we place one of each panel type and then adapt the color counts, their effects even out. But now consider a configuration like these ones in our design chart, where there is just one free tile. We begin with our total color counts completely balanced, and then start placing all of our parity conserving buildings like accumulators, substations, and roboports. The color numbers decrease evenly, so after placing all of them we are still left with a balanced color count. Next up, we place our 1x1 tile. One of the colors, doesn't really matter which, needs to decrease by 1. So now there's some slight color imbalance. Finally, let's place down the panels. Let's use some variables A, B, C, and D to encode the actual amount of each type of solar panel. Then, because we know how many tiles of each color there must be, we can write down some equations to solve for the quantity of each solar panel type. And here's where the beautiful realization comes in. If we take the first equation and subtract it from the fourth and do some algebra, we can show that D minus A equals 1/3. But that can surely not be, because A and D are counts, so they need to be integers. And no two integers exist that you can subtract from each other to get a rational number. We have shown then that with solar panels, it's impossible to fix a one-tile color imbalance, so those configurations with one single 1x1 tile left are definitely not feasible if the array is an even-sided square like a 50x50. This might not seem that big of a discovery, but it narrows things down significantly, particularly because I can already tell you that the 10 free-spaced A316 is really easy to find, even with no initial guess and using an average solver. After all, 9 substations are more than enough to ensure all grid requirements by themselves, and even still we have 10 tiles to spare, which is a lot. What that means is that everything under 8316 kilowatts is automatically outclassed. So in order to improve on the A316 solution, we have two potential routes, either A333 or A358 kilowatts. And look at A358 for a moment. The only potential improvement is to bump it up to here, at A383. But the problem with that one is that it only has 6 substations, and on top of that, 0 tiles to spare. That means absolutely no auxiliary medium poles, so we would need to comply with all 3 electric constraints with just the 6 substations by themselves. And I don't have mathematical proof here, but I'm almost certain that it is impossible to cover a 50x50 square with just 6 substations, let alone meet the connectivity or tileability requirements. So look at that, we still have not written a single line of code for the solver, but we have already narrowed it down to just a couple of options. Quite a useful chart, isn't it? Although, in all honesty, I did tell you that the A316 is possible, but still I think the point stands. Okay, so now that we have defined the problem, studied the constraints, and have a general idea of what the optimal solution could look like, it's finally time to put some numbers behind our ideas. For this section we are going to need to get a bit more technical with the linear algebra. Nothing super fancy, but concepts like matrix multiplication and matrix transposition are important here. The first thing we need is a proper mathematical way to encode what our design looks like. And for that, we are going to use a set of variables which we collect inside a state vector x. There's more than one way to go about doing this, but the most effective way I found is using a large set of binary variables. These encode whether or not there is a building at each possible position. I'm going to use a 4x4 mini panel to show you what I mean. Let's number the tiles from 0 to 15, and then let's create 16 variables, one for each tile, which will encode whether or not a solar panel has its lower left corner at that particular tile. For example, if we place one solar panel at tile 4, we encode this configuration as x sub 4 equals 1 and everything else equals 0. Now let's go the opposite way. Let's visualize a configuration where x sub 1 and x sub 4 equals 1 and the rest equals 0. This means that there are two panels, one with its lower corner at 1 and the other with its lower corner at tile 4. This configuration is not physically valid, obviously, because they overlap, but do not worry too much about that. The important thing is that this set of variables encodes all possible designs we could come up with. Additionally, we are going to need another 4 sets of 16 variables to encode the positions of the accumulators, substations, roboports, and medium poles. We can combine all of these sets in a single X vector that uniquely identifies our design. For the actual 50x50 square, the vector gets pretty large at 12,500 elements. It's worth mentioning that some of these variables are actually dummies, because for example, we are only placing one roboport and in the center of the square, so we already know that in the roboport slice, x sub 1173 is equal to 1 and everything else is equal to 0. But do not worry too much about the extra variables, because the algorithm we are going to use is actually pretty smart and will easily pick up on redundancies and get rid of them. So it's better to fully define things as we have, just for the sake of consistency across all building types. The next step is to properly define the optimization metric in terms of the newly created variables in vector x. Now, because we are using binary variables, we are going to need a mixed integer linear programming solver algorithm to find our optimal solution. Mixed integer means that it will be able to deal with variables that are integers or even binary. And in this context, by programming, what we mean is optimization. This type of solver can deal with enormously large variable counts, but the caveat is that it's linear. That means that our constraints and metrics need to be linear equations as well. For example, this equation is a valid linear constraint, and similarly, linear inequalities are supported too. But things like quadratics, exponentiation, or trigonometry are definitely not allowed. I bring this up because our maximum continuous power formula involves a call to a minimum function, and that breaks linearity, so we cannot use it as is. Fortunately, there is a useful workaround to linearize things in this case. The key to this is the creation of a new variable set. Then, on this variable, we impose the following two linear constraints. And then, finally, we say that the maximum continuous power is equal to set. With this little trick, we have been able to transform our non-linear expression into a set of three linear equations and inequalities, which the solver can handle no problem. The cost to this transformation is the definition of one more variable, but that's a relatively small price to pay. Finally, in order to use the variables that we have inside the x vector, we can say that the number of panels equals the sum of all variables within the panel slice, and the number of accumulators equals the sum of all variables within the accumulator slice of vector x. In this way, we have the optimization metric fully defined as a linear function of the variables that we chose. And now the next thing we need is to define the constraints. These are going to ensure that there is no overlap, that the electrics cover the entire array, that a roboport is placed in the middle, and so on. We are going to start with that last one. As mentioned before, we only need one roboport and it's going at the very center. So for our first set of constraints, we can say that x sub 1173 equals 1, and the sum of every other x within the roboport slice that is not 1173 is equal to 0. This is the mathematical way to tell the solver that we only want one roboport and we want it at the center. Next up is the overlap. As you know, we cannot allow two buildings to be on top of each other. Shout out to this paper by Sasha Kurth, which is where I first read about this whole binary approach to packing problems. The idea is similar to what we did before with the colors to show that some configurations are not possible. But now, instead of 4 colors, we are using as many colors as tiles there are in our array. Then there is only one tile of each color, which means each color or each tile can only be used once. If you recall, before we got 4 equations, one per color, and now that we have 2500 colors, we are going to get 2500 equations. To see how this works, let's go back to our mini panel. Now let's use accumulators. The first accumulator, which is encoded in the variable x sub 0, uses 4 tiles with numbers 0, 1, 4, and 5. The second accumulator, x sub 1, uses tiles 1, 2, 5, and 6. See the idea? Now let's keep doing this for all possible accumulators. And then, just as before, we are going to write down equations to compute the amount of times each tile is used. Because there is so many of them, it's much more compact to write this as the linear system a times x is smaller or equal to b, where now a is a matrix, x is our variable vector, and b is another vector which represents how many times each tile can be used. At each row of matrix A, we find mostly zeros and then a few ones when an accumulator uses that particular tile. For example, look at row 5. As you can see, the accumulators that need to use type 5 are accumulator 0, 1, 4, and 5. So it is at those particular positions that row 5 is going to have 1s instead of zeros. What this is telling us is that those 4 accumulators are actually incompatible with each other. Because they all share tile 5, we can only have one of them at once, otherwise there would be some overlap. In other words, the vector resulting from the multiplication a times x encodes how many buildings are on top of each particular tile. So for there to be no overlap at all, we need all the components of this vector to be either 0 or 1, which is what b encodes. On my animation here, I've only been showing accumulators, but obviously we also have solar panels and other buildings, so our matrix A should account for those too. In the end, because we have 12,500 variables, we end up with an A matrix that has 2,500 rows, 1 per tile, and then 12,500 columns, 1 per potential building we could place. Next up, we are going to tackle the restrictions corresponding to the electrics. As I mentioned before, coverage, connectivity, and electric tileability are quite a headache to deal with. Fortunately, I did come up with a robust formulation for coverage at least. Just as we did before, we can define a matrix E which encodes which tiles are affected by each substation or medium pole placement. Just a moment ago, I mentioned that the vector that results from the product 8 times x represents how many buildings are on top of each particular tile. Now, we are going to have another vector which results from the multiplication E times x, which represents how many substations and medium poles are covering each particular tile. I hope you can see the parallelism here. Now, here's where the tricky bit comes in. With E times x, we know how much each particular tile is being covered by electricity. But in fact, what we really want to know is how much each particular building is covered by electricity. So what we need is a way to relate individual tiles to full buildings. And that's where our matrix A comes in again. Because when we transpose it, we get another matrix, A transpose, which encodes the tile usage of each building. So then, if vector F indicates how much coverage each tile is getting, A transpose times F indicates how much coverage each particular building is receiving. Let's call that vector D. And then, if we substitute the formula for F, we see that D equals A transpose times C times X. With this knowledge, finally, we can write down an equation for the coverage constraint, which takes the form of X minus D must be smaller than B prime. X is our variable vector which encodes whether or not each particular building exists, and D represents how much coverage each building is getting. Finally, let's define B prime as the amount of coverage each building needs. B prime is equal to 1 for solar panels, accumulators and roboports, and 0 for substations and medium poles, because they do not need coverage themselves. For example, let's think about the very first equation of this set. X sub 0 minus D of 0 must be smaller than B prime of 0. X sub 0 encodes a solar panel, so B prime of 0 is 1. If the panel exists, X sub 0 equals 1, and if it's getting at least 1 unit of coverage, meaning D of 0 is greater than 0, then the configuration is valid and the equation holds. Similarly, if our design does not have that panel, meaning X sub 0 equals 0, then the constraint is fulfilled automatically. On the contrary, if the panel exists but it's getting no coverage, meaning D of 0 is 0, the inequality does not hold and the setup is invalid. And basically that's how we deal with electric coverage. It's definitely another step up in terms of difficulty compared to overlap, but it's still kinda manageable. However, connectivity is where this binary-based formulation starts being problematic. It turns out that it's pretty hard to find linear constraints to ensure the connectivity of a graph, let alone one that has two types of connective elements, substations and medium poles, and also an undefined number of them. I was able to eventually find a workaround, but it involved some significant compromises. In particular, things become considerably more manageable if we fix the position of at least one network element, which we are going to call the root of the network. The root can be placed wherever we like, but once we decide on that, it's fixed and cannot be changed. I chose to place a substation in the lower left corner. Then we go through the complete grid in a predefined order that starts at the root, and whenever we encounter a connective element, we check whether or not that network element is connected to the root or another previously encountered element. This method provides a sufficient condition for connectivity, but crucially not a necessary one. For example, here both network A and network B are valid in terms of connectivity, but our equations will fail for network B, because the second substation is encountered before the one that actually connects it to the root. So in fact, this method of proving connectivity is actually discarding valid solutions. However, I wasn't able to find anything better which does not involve increasing the variable count very significantly. My bet here was that the pool of candidate 50 by 50 arrays is large enough that optimal solutions exist even with this over-constraining method. Fortunately, as you know, the gamble did pay off in the end, which I'm extremely happy about. For the actual equations, we can reuse the idea from the coverage restriction, albeit with a different main matrix. Just as we did with coverage, X encodes whether or not each building exists, C times X encodes how much connectivity that building is getting, and B double prime indicates how much connectivity that building needs. So for example, solar panels do not need connectivity, but substations do. Construction of matrix C is a bit more complicated than A or E, and I unfortunately don't have time to go into the details here. The video is already long enough. But if you're interested, you can always go down to the description and have a look at the GitHub link I provide there, which contains all the code I made and used for this video. Finally, the last constraint we have to deal with is the tileability of the electric network. It might not seem very hard, but it's actually even harder than connectivity. And at this point I was really tired and I decided on a straightforward solution to this. Let's just force a placement of 3 substations at 3 of the corners. We already need to force one for the connectivity requirement, and fixing 2 more solves the headache that is tileability. Just as with connectivity, that provides a sufficient but not necessary condition, because there might be a perfectly tileable network with substations away from the corners. But again, I gambled that this stronger than necessary restriction was not going to damage the solution pool enough to impede an optimal solution from showing up. And once again, it paid off. So far, I've given you a vertical slice of the ideas it takes to solve this kind of problem, but I did not stumble upon all of this right away. It took a lot of trial and error to slowly narrow things down to something that works. So let's finally see it working. We're going to have 2 parallel optimizations, depending on whether or not we decide to replace the Roboport after the building stage is completed. The optimization run to the left considers that the Roboport will be permanent, while in the run to the right we assume that it will be eventually replaced by 4 accumulators, resulting in some extra power. I configured my solver to run using 20 threads of my CPU and allowed it to keep going for a few days. With that, we managed to get up to 8,274 kilowatts for the permanent Roboport setup and 8,333 kilowatts for the Roboport free setup. These are already pretty solid results, but there was something still nagging me. They really weren't the best. We already know that the best plausible result for the Roboport free configuration is 8,358 kilowatts, at least with base quality electric components. And as for the permanent Roboport configuration, although values are lower overall, and that 8,274 kilowatts is pretty close, both 8283 and 8316 are within the realm of possibility, although that last one requires a 5 substation, 10 medium pole grid, which is really pushing the limits. So for the sake of my own perfectionism, I had no choice but to go on a quest to find these better results. The key to this final task was splitting the problem in 2. First, finding as many good electric networks with valid connectivity and tileability as possible, and then going through them one by one to see if they allow good packing of the remaining buildings around them. This strategy proved successful relatively soon for the Roboport free setup, and I found a real instance of our 8,358 kilowatt theoretical best after manually scanning around 200 networks the solver came up with. And that's the setup you've been seeing throughout the whole video. I promised we would get here eventually. The permanent Roboport setup though was way more restrictive in terms of the network, so I had AI write a few scripts to test and improve the networks on a much larger scale. After a few weeks of implementing changes and going back and forward, and also lifting some of the heavier restrictions, the problem finally relented and spat out something that matched the 316 kilowatt theoretical best. So yeah, these finally are the results I wanted. Early to mid game, you probably want to go for this one, and then for larger bases where optimization is more important, it's probably better to go for this other one and then eventually take out the Roboports to save on UPS and also get a bit more extra power per unit area. You can find both blueprints in the description. With that, and after like 3 or 4 months of working on this, I consider this project to be finally completed. I might eventually do a part 2, but before I let you go, there's some important stuff I should mention. First, as you can see, both of the designs used a 50 by 50 square as their base, but if you check out the blueprints below, you'll see that the actual standalone tile is not square. I decided to allow this in optimization because it kinda looks cooler when the tile looks like a weird spaghetti puzzle piece, but still fits perfectly when placed next to itself. This also gives a bit more leniency to the solver. Also, I kinda forgot about the radars. When going for full expansion, you probably want to blueprint a 4x4 of these tiles, and then take out 4 accumulators in a 2x2 pattern and replace them by 1 radar. These setups I provided you with are slightly accumulator rich anyway, so 50/50 optimality will be maintained. And now that we mention optimality, on that note, remember that our design charts guarantee optimality for these setups only at the 50 by 50 level. For example, if we placed 4 tiles together to get a 100 by 100, that configuration would not necessarily be optimal anymore, although it's pretty close. That's the case because the bigger the array, the more we can hone in on the perfect ratio, and also because the bigger the array, the more efficient we can be with the electrics. But if we truly wanted an optimal 100 by 100 tile, we would need to solve a much bigger problem, with way more variables. 50 by 50 is a solid compromise between how close we can get to the ratio and how big the model gets. Finally, the current version of the code in GitHub uses an algorithm called HICE, which is a freely available solver accessible from Python. I personally used a different algorithm with parallel computing capability, which makes it much faster, but it's sadly not available for everyone. So if you want to run this, you'll have to make do with the slower highs or find a license for a better solver for yourself. In any case, remember that this is a tough problem. Do not expect to go in and get results in 5 minutes. Good optimization runs take hours or even days, especially on single core. And as a final warning, the code is not super fleshed out. There's a lot of trial and error and barely any commenting. Particularly the two-stage process I used to bridge the gap from the original solution to Optimality contains a lot of unsupervised AI code, which does work, but is messy at best. And I guess that's all from me today. I hope you found this video useful or at least interesting. It did take a while to make, I won't deny that, but it was a very fun challenge to tackle too, and I learned a lot. So much in fact that I might do a part 2 at some point. So if you liked it, consider subscribing, hitting the like or hype buttons, or sharing the video. It helps a lot. Thanks!